Welcome grade 9 students to this video on efficiency. This is going to be just a short little video to go through the efficiency formula. First thing we're going to need to do is take a look at what actually is efficiency in the first place. Well, in every single process that we've got, so if this is a process, you're going to have energy from a particular energy store go into this process, and energy is going to go out of this process. The thing is that not all the energy that goes into the process goes out of the process in the store that we want. There is going to be some of the energy that is going to go into some other store. Now this could be, let's say, like a thermal store to the surroundings, but all the energy that is coming in, 100% of the energy coming in, is coming out in these two. And our efficiency is how much is coming out in the manner that we're looking at. So if we had 100% of it coming in, and we had 20% of it coming out, and 80% going to other sources, this would be 20% efficient. But let's say instead of 20% was coming out, let's say it was 75% was coming out in the way that we wanted it. That means 25% would be coming out in other stores. So if we were to write the efficiency formula, now this is on your formula sheets. You do not need to memorize this. It is written as energy, the output divided by the input multiplied by 100. Now again, that is the energy output that we are specifically looking for, not the energy output total, because the total is going to be exactly the same as how much in. This is the energy out, the stuff that we're hoping to find. So let's take a look at our first example here. A particular appliance uses 25,000 joules of energy to produce 17,500 joules of useful energy output. So again, that efficiency is just the output divided by the input multiplied by 100. So to find that efficiency, that's the 17,500 joules that we got coming out. That's useful for whatever this device is using, but a full 25,000 is going in. Multiply that by 100. Now, when you type this in your calculators, and you should be typing this in your calculators, you should be getting in the neighborhood of 70%. Now, the other 30% is coming out of this process as well. It's just that that other 30% is not in useful forms, or it's not in the intended form that we have. So if we were to take a look, let's say, at the next question. A 60-watt light bulb running for 4 hours gives off 42,300 joules visible light. What is the efficiency of this bulb? Well, the first thing we need to know is how much energy is actually coming into this bulb. So the energy, as we've discussed before, is power times time. The amount of energy, that means it's a 60-watt light bulb multiplied by, now because we're dealing with joules, we need to have the energy in joules, so that's going to be watts and seconds. 4 hours is 14,400 seconds. We get that by multiplying 4 hours by 60 minutes per hour by 60 seconds per minute. And so you find that the amount of energy that's actually going into this light bulb is 18,400 joules of energy. But it's only giving off 42,300 joules of visible radiation, right? Going from its electrical pathway coming into the process to a radiation store outside of the process. So to find the efficiency, we're going to take a look at that. Again, the output over the input multiplied by 100. So we get 42,300 joules of visible light and 86,400 joules of electrical input. Times by 100. Now, a little hint here when you're dealing with the efficiency formula, you're never going to wind up with an efficiency greater than 100. Because you can only get out what you put in. So if you wind up mixing up these numbers and you wind up getting a number greater than 100, you know you got to flip them. But this works out to 4.89%, which means this is probably an incandescent bulb. Okay, taking a look at the next one. How much does it cost to run the light bulb if electricity costs 6.5 cents per kilowatt hour? Well, remembering that, again, energy is equal to power times time, but we're looking for the amount of energy in kilowatt hours. Now, we have done this before, both in grade 8 as well as a little in grade 9 already. And so we need the light bulb, that 60 watt light bulb, is the same as 0.06 kilowatts. So power is 0.060 kilowatts. And the time is still 4 hours. So the amount of energy is going to be 0.24 kilowatt hours of energy. That is the same as that 86,400 joules. Now, if we multiply that by 6.5 cents per kilowatt hour, you're going to wind up with 1.56 cents. So how much money is wasted on energy other than light? Well, we're going to take that 1.56 cents, and now if you multiply that by the 4.89%, that's 4.89 divided by 100. I'm going to write that down actually, 4.65 times 4.89 over 100, because that's what percent is. You wind up with 0.07 cents. That's how much is actually being used on light. So the amount that's being used on things other than light is going to be that 1.56 minus the amount we're actually using in light. You get a 1.49 cents. Now, an alternate way we could have done this was simply to take that 1.56 cents and we're going to multiply it by the 95.11% of the amount of energy that's going to something else. And that will get you this number as well. So, what I need everybody to do is to work on page 329, numbers 1 to 3, and 331, numbers 2 through 4 in your textbook. And if you got any questions, let me know. Take care and have a great day.